Recursion is a pretty confusing topic if you're just starting out, but in computer programming, some problems are much easier to solve using recursion. Though it's not without its trade-offs, recursion is an essential tool for every programmer to learn and master. In this video, I want to explain what recursion is in simple terms with real-life examples. Let's get into it. What is recursion? In short, it's a way to solve a larger problem by having the solution function call itself to get the answer. And it especially helps with nested structures, as we'll see in the examples. Now, if you're thinking clearly, having the same program call itself sounds like a recipe for disaster. And that is true if you don't handle recursion correctly. So let's briefly talk about the structure of a recursive program or algorithm to help prevent this common issue. Recursion has two main parts. Number one, the base case. This is some logic where the recursion stops and the function returns, usually when something is empty or doesn't meet some criteria. Number two, the recursive call. This is the place where the data passed into the function is usually made smaller and where the function calls itself. The recursion will take place until the base case is reached. The functions will return and bubble up as each hits its base case, and once the last function returns, the program will end. If the base case is not set up properly, the program will never end, and then the programming language's call stack limit will end the program with some sort of stack overflow message. Let's look at some real-life examples of recursion. Example number one, looking up a word in a dictionary. Looking up a word in the dictionary can be solved recursively. Each letter starts the alphabetic search from A to Z all over again until all letters are found. Let's use a simple example, dog. First, we start by looking for D in the dictionary. We start at the beginning with letter A, find B, then C, and then D. And then we have the first letter in place. Now we start the process over by looking for the second letter. We start with A again and then go all the way up to O. Of course, our brains know how to optimize this process, so we might jump forward. But it's the same idea. We find O, and our second letter is established. Now we look up the third and final letter, and the search begins at A, and we go up to G. Once we find G, we see the definition, and we're good to go. D, O, G. In this example, the base case is finding the current letter in the right position in the dictionary or not finding the letter. Maybe we've spelled the word wrong or it isn't in our copy of the dictionary. And the recursive call is finding the next letter in the dictionary. Let's look at another example. Looking for a file in a directory is also a recursive process. Let's imagine you place a song file called bestsong.mp3 in a folder called My Songs, and that folder is in another folder called Music. So our folder structure looks like this: Music, then My Songs, then bestsong.mp3. How can we find out if the file bestsong.mp3 is in our music folder? Recursion. We begin with the root directory we want to search in. In our case, it's called music. We check if it has the file called best song. This is our base case. If it doesn't, we see if there are any other directories in the music folder and check each of those. In our case, we see My Songs is a folder, and we open that folder and then repeat. We check for bestsong.mp3 and we find it, and we've hit our base case and we end the search. Recursion for the win. So why is recursion helpful? Recursion is helpful because it makes solving certain types of problems a lot easier to solve conceptually. While solving the same problem iteratively is possible, it can often be a lot more complicated. For example, we could use two stacks, and then the first stack has something in it and we pop one off. If it has any children, we push them onto the second stack. There are a few common pitfalls of recursion. The first main pitfall of recursion is wrapping your head around a function calling itself and how to handle the data. Hopefully this video has helped simplify the concept and will aid you in learning and applying it to more types of problems and data structures. The second main pitfall is receiving a maximum call stack error. This is common if your base case is not correct. For example, if you never end your recursion at some fixed point, it will continue to run and you'll overload the call stack as your unreturned functions build up. You can test this in a few seconds like this. If you get a call stack exceeded error, that means you have an infinite loop and you should recheck your logic to make sure your base case makes sense and is in the correct place. At least one of your base cases should be hit eventually. Another common pitfall is having the incorrect logic so that your solution function produces the wrong answer. If you try to get the maximum tree depth, but you don't call max on the recursive function's results, you could end up with the wrong answer. I recommend slowly walking through a simple problem that covers the main edge case to test your code if this is happening. Trade-offs. The simpler mental model isn't without its costs. The biggest trade-off is sacrificing memory. It's often easier to think through a problem recursively where it applies, trees and graphs, etc. But it costs more memory to run the solution recursively because the calling functions are left hanging before their children functions return. So if it's a large data set or a complex algorithm with many executions, it can build up extra memory. I hope this was a helpful explanation of recursion using real-life examples. As usual, I'll leave some helpful links in the description, and thanks for watching.